now that we've talked about the difference in the properties between compounds that have ionic bonds and covalent bonds, I think it's really important to be able to compare the strengths of different ionic compounds, or the bonds in different ionic compounds. Coulomb's law is what we're going to be using to compare those relative strengths. So Coulomb's law, again, is a simple equation that can describe the relative strength of an ionic bond. And it actually is related to two different things. Bond length, which we'll see in a minute, has everything to do with the size of your atoms, and something called charge separation, or how strong of a charge your ions have. Now, the equation that actually represents Coulomb's law is down toward the bottom of the screen. Force is directly proportional, that's that weird little funky, like ribbon-looking symbol, directly proportional to Q1 times Q2 divided by D. Now, to make sure that you know what those terms are, when we're talking about bond length or atomic size, we're referring to D. D is the distance between the nuclei of our two atoms. And when we're talking about Q1 and Q2, we're talking about this charge separation, or how strong those two charges are. Q1 and Q2 refer to the charges of the different ions involved here. So let's take a look at one thing at a time. Let's start with this bond length, or atomic size. Off to the side of your screen, you're going to see 4 different examples of different cations bonding with the same anion chlorine: lithium, sodium, potassium, and cesium. Now, the periodic trend, of course, as you go down the periodic table in that same family, is that the atom or even the ion is going to get larger, and that's due to them having more shells of electrons. But notice also what it does to the different distance between the nuclei. Tiny little lithium bonded to chlorine has a distance of 241 picometers, whereas cesium bonded next to chlorine has a distance of 348 picometers. Bigger atoms simply mean a bigger distance. So again, just to kind of recap, bond length is officially defined as the distance between the two nuclei involved in a bond. Now, here's some interesting information. We can actually take these compounds and melt them, and what we're going to be measuring is their melting point. And that's the temperature at which we first start to see them melting. Now, notice lithium chloride is not even registered here, but sodium chloride 801, potassium chloride 770, and cesium chloride 645. Now, again, take a look at the picture. What happens to the melting point as the distance between the nuclei increases? Well, that's exactly right. The greater the bond length, the weaker the bond strength. In other words, cesium chloride, it has the biggest bond length, but it takes the least amount of energy, though it has the lowest melting point, in order to get that sucker to melt. So the larger the distance between those nuclei, the weaker the bond is going to be. So again, big atoms mean low melting point. And we can take a look at that equation just one more time, being force is directly proportional to the charges divided by the distance. As distance increases, force decreases. Now let's take a look at this charge separation business. Again, 2 compounds are shown to you on the screen. I have aluminum fluoride and aluminum oxide, and their melting points are also shown to you. Now, fluorine and oxygen are in the same row of the periodic table, so they have approximately the same number of shells of electrons, and they're not really that different in size. So you're really not going to be able to compare them simply based upon their size. This is really a charge argument. In order to kind of fully explain this, I need a number line. And I'm simply going to plot where the ions, the individual ions, aluminum, fluorine, and oxygen belong on this number line according to their charge. So of course, aluminum has a positive 3 charge, and fluorine has a -1 charge. And then if I take a look at aluminum and oxygen, oxygen has a -2 charge. So the simple question you need to ask yourself is, which pair of ions here is the furthest distance apart on this charge number line? Well, you're probably figuring it out. Yes, aluminum and oxygen are the furthest distance apart on this number line. That means they have the largest charge separation, or the largest difference between their two charges. And if you kind of cross-reference that now against our table of data, well, the aluminum oxide has the highest melting point here. So the higher the difference in the charges, the stronger the bond is going to be. It simply takes more energy to get that aluminum oxide to melt because they have the strongest difference between those charges. Again, take a look at this lovely equation. Force is directly proportional to the two charges multiplied divided by the distance. So as the charge numbers go up, the force between those charges go up as well. Now, before we leave this section, I think it's important that we practice. So I have two sets of compounds, three of them all together, and I would like you to try and put them in order of increasing melting point. So the first compound would be the one with the lowest melting point. It takes the least amount of energy to get it to melt. And the last compound would be the compound that it takes the most amount of energy, highest temperature, to melt. Push pause, and when we resume, you'll see the answers. All right, welcome back. I think it's time that I show you some answers to these lovely problems. Keep your fingers crossed. Correct answers for number 1 be sodium fluoride, followed by sodium oxide, and then sodium nitride. The difference between these and the way that you would figure this one out is charge separation. The fluorine and the oxygen and the nitrogen all have different charges. The nitrogen has the strongest charge of all of those negative ions and therefore should take the largest amount of energy to get it to melt. In problem number 2, we have NaCl, MgCl2, and AlCl3. Again, you're looking at charge separation. The aluminum has a positive 3 charge. It's much bigger than the magnesium with a 2 plus and sodium with a 1 plus. So the aluminum chloride should take the largest amount of energy to get it to melt.